Okay, dear children, today we'll be starting with the second chapter of your science one, that is periodic classification of elements. Now, classification is a word which you have studied in ninth standard. You had studied classification of plants, right? So, when we say classification, what does it mean actually? It means arrangement into different groups. For example, if you go into your kitchen, you will find that all the different utensils are placed in a specific way. The place where you have to keep the spoons, you will find obviously spoons over there. The plates will be in one place, the cups and glasses will be in another place. Similarly, when you open your wardrobe or your cupboards, you will find that different clothes are arranged in a different way. Now, what happens by this arrangement? When you arrange things, it is easy to understand them. It is easy to know more about them. It is easy to study them, right? So, we classify elements because studying these elements become easy. So, the main point here is we always wanted to know more about the elements. See, you have a chapter called carbon compounds. You studied last year also, and it is there this year also. This carbon compounds is a small part of the whole history of carbon. Carbon is very vast if you go to study it further. It never ends. The more you go into higher studies, the more you will learn about carbon. Similarly, every element has its own story, has its own background, its own physical properties, chemical properties. As you go into higher studies, you study more. Okay, now today in this scenario where we have a lot of elements with us, so we have around 118 known elements. Okay, and these 118 known elements were classified, are classified in a particular way. Do you think that these 118 elements were known even earlier? No. If you look into the year 1800, okay, so we will just 1800, only 30 elements were known, and these 30 elements were the simplest elements which were discovered that time, and many scientists tried to classify these elements. And we study some important classifications because these were the first classifications which were done. Today we have around 118 elements which are classified in the modern periodic table. So going into history, you have the earlier scientists. The first scientist, Dobereiner, a very important man in the field of classification of elements. He was a German scientist, and Dobereiner classified these elements in the year 1817. Okay, so in the year 1817, Dobereiner, who was a German scientist, classified the elements. So you have to remember the name as well as the spelling. Dobereiner, Dobereiner. Who he was? He was a German scientist. In which year? 1817. He gave an idea to classify the elements. He suggested that the properties of the elements are related to their atomic masses. What did he suggest? He suggested that the properties of the elements are related to their atomic masses. It means that the atomic masses decide the properties of the elements, or in another way I can put it that the properties of the elements were dependent on their atomic masses. So he made groups of three elements. He made groups of three elements having similar chemical properties, and he called them triads. The very important word. He called them triads. So he made groups of three elements each having similar chemical properties, and he called them triads. He arranged the three elements in a triad in an increasing order of atomic mass. So we have to get these 3 points, very important. Dobereiner made groups of 3 elements each having similar chemical properties and called them triads. Dobereiner made groups of 3 elements each having similar chemical properties and called them triads. He arranged the 3 elements in a triad in an increasing order of atomic mass, and he showed that the atomic mass of the middle element was approximately equal to the mean of the atomic masses of the other 2 elements. Now again, the first part is quite easy, but the second part is mathematical, and to understand that we have to see exactly what these triads are. So when I say triad, it is a group of 3 elements. So what he did, he arranged the 3 elements in the triad, right? So he made groups of 3 elements each having similar properties, chemical properties, and called them triads. What did he do? He made groups of 3 elements each having similar chemical properties and called them triads. He arranged these elements, 3 elements, in a triad in the increasing order of their atomic mass. And what did he show? He showed that the atomic mass of the middle element was approximately equal to the mean of the atomic masses of the other 2 elements. Now to understand this, let's look into the table. You have 3 elements here: lithium, sodium and potassium. Okay, lithium, sodium, potassium. The atomic mass of lithium is 6.9. The atomic mass of sodium is 23, and the atomic mass of potassium is 39.1. Now if you take the mean, that is the average of the atomic mass of lithium and the atomic mass of potassium, so what is the average? 6.9 plus 3.9 upon 6.9 plus 39.1 upon 2, that is equal to 23. Let me repeat. The atomic mass of lithium is 6.9. The atomic mass of potassium is 39.1. If we take the mean of the atomic masses of lithium and potassium, we get 23. How do we do it? 6.9 plus 39.1 upon 2 is equal to 23. So we can analyze it again. Let's look at it again. We have 3 elements in the triad. What are they? Lithium, sodium and potassium. Atomic mass of lithium is 6.9. Atomic mass of potassium is 39.1. And if you take the mean, that is the average, we get 6.9 plus 39.1 upon 2 is equal to 23. Yes, 23 is the atomic mass of sodium. Now did you get it? Let's look at the statement again. The atomic mass of the middle element is approximately equal to the mean of the atomic masses of the other 2 elements. Okay, very important part of the statement. He showed that the atomic mass of the middle element was approximately equal to the mean of the atomic masses of the other 2 elements. So similarly, if you take the second one, calcium, barium and strontium, you will see that calcium, barium and strontium, calcium has 40.1, barium has 137.3 as its atomic mass, and if you take the average, the strontium atomic mass comes to 88.7. Now when you analyze this further, you see that 88.7 is not very close to 87.6. okay, it is around 88, you can say like that, but it is not exact value, right? As well as, though Dobereiner used the word approximately, if you look at 88.7, it goes to approximation of 89, and if you look at 87.6, it goes to approximation of 88. So there is a lot of variation. If you see other triads, chlorine, bromine, iodine, you can see bromine, the average is 81.2, but bromine's atomic mass is 79.9. So you see there was variation. So what happened is, initially Dobereiner's triad proved to be successful in the classification of some elements, but later when many other elements were discovered, they could not be classified into triads. That is why Dobereiner's law failed. So let's have a recap. Dobereiner was a German scientist. In the year 1817, he suggested that properties of the elements are related to their atomic masses. He made groups of 3 elements each having similar chemical properties and called them triads. He arranged the 3 elements in a triad in the increasing order of their atomic masses, and showed that the atomic mass of the middle element was approximately equal to the mean of the atomic masses of the other 2 elements. For example, lithium has an atomic mass of 6.9. Potassium has an atomic mass of 39.1. If we take the mean of the atomic masses of lithium and potassium, we end up with an average of 23, which is the atomic mass of sodium, which is exactly the atomic mass of sodium. But when you go further and look into other triads like the triad of calcium, strontium, barium, or chlorine, bromine, iodine, the mean is not equal to the atomic mass of the middle element. That means that when new elements were discovered, they could not be classified into triads, and that is why Dobereiner's law failed. So after Dobereiner, there were many other scientists, and one of the prominent scientists was Newland. John Newland. In the year 1866, Newland, he arranged the elements in the increasing order of atomic masses. So as you see, Newland also arranged elements in the increasing order of their atomic masses. And he started with the lightest element, hydrogen. Okay, lightest element, hydrogen. And he ended with the heaviest element, that is the thorium, which was known at that time. That is thorium. Thorium was known at that time as the heaviest element. He found that when he arranged the elements in the increasing order of the atomic masses, every 8th element had properties similar to those of the first. This is a very important part which you should know. Newland arranged elements in the increasing order of their atomic masses. It started with the lightest element, hydrogen, and ended with thorium. He found that every 8th element had properties similar to the first. Newland arranged elements known at that time in the increasing order of their atomic masses. It started with the lightest element, hydrogen, and ended with thorium. He found that every 8th element had properties similar to those of the first. For example, if you look into the table, you see it starts with hydrogen, right? And if you count 1, 2, 3, 4, 5, 6, 7, 8. So fluorine is below hydrogen, chlorine is below fluorine. So that way, sodium is below lithium. If you start from lithium, start counting from lithium. Lithium is the first, beryllium is the second, boron is the third, carbon is the fourth, nitrogen is the fifth, oxygen is the sixth, fluorine is seventh, and sodium is eighth. So the property of sodium will be similar to the property of lithium. That is meant by the sentence that every 8th element had properties similar to those of the first, right? So you can see that even beryllium and magnesium, they have certain similar properties. Beryllium and magnesium have certain similar properties, but you see that further the properties don't match that much. like okay, oxygen is there, which is a non-metal we can say, but it is a gas, and below that there is sulfur, and the next element below it is iron, which is a metal, so it is totally gone awry. So the point is, even Newland, uh, you know, there were certain limitations in Newland's octaves, and it was applicable only till calcium, that is here calcium till calcium, and after calcium the Newlands law was not valid. Now here one interesting point is that we also call this law as the law of octaves, for the simple reason that when we study this law we understand an interesting point, that is let's look into the table. Yes, so here it comes. Yes, so we understand an interesting point, that there is repetition after every 8 element. So this is, it sounds something like our Indian classical system, where you have sa re ga ma pa da ni, then comes sa, right? Sa re ga ma pa da ni sa. So count in your fingers, sa re ga ma pa da ni sa. So sa comes 8, so which is similar to the first, and again if you start sa from there, again re will come, and ga ga, so it goes like that. So that is called saptak, right? So the frequency of sa in the beginning is matching with the frequency of the next sa, which comes 8th. And like there is Western music, there are 7 notes, right? So here we call it the also the Newlands law of octaves. I hope you followed this. You have to write the answer in such a way as I'm going to repeat now. Newland was an English scientist. John Newland was an English scientist. He classified the elements according to their atomic masses. In the year 1866, Newland arranged the elements known at that time in their increasing order of atomic masses. It started with the lightest element, hydrogen, and ended with thorium. He found that every 8th element had properties similar to those of the first. For example, sodium is the 8th element from lithium, and both have similar properties. Also, magnesium shows some similarity to beryllium, and chlorine shows similarity with fluorine. And Newland compared this similarity with octaves of music. He called the similarity observed in the 8th and the first element as law of octaves. Now you also have to write limitations, that this law was found applicable only up to calcium, and he fitted all the known elements in the table of 7 into 8, that is 56 boxes, and then he tried to place some more elements in the same box. For example, cobalt and nickel he placed in the same box, and cerium and lanthanum he placed in the same box, though they had very different properties, right? So if you look in the table, cobalt and nickel is together, cerium and lanthanum is together, and so he placed elements with different properties under the same note in the octave. And when you place an element with different properties, obviously the law will not be valid, and that is why Newland's law was not valid when more and more elements were discovered. Okay, so when new elements were discovered, his table did not have any provision to accommodate these newly discovered elements. So that is Newland's law of octaves. Can be asked for 2 marks. You have to write the theory as well as the table, at least till calcium you should know, right? That is the end of the topic. Thank you.